Hello, everyone. Today, I'm very happy to have the opportunity to share our work at LA DataCon. I'm Zitao Liu from TAL Education Group, and today my talk is a practical guide to robust multimodal machine learning and its application in education. So here's a brief introduction about myself. So right now, I'm the head of engineering at Xueersi one-on-one at TAL Education Group, and my research area is AI education and multimodal machine learning. And before joining TAL, I was a research scientist at Pinterest, and I got my PhD in computer science from University of Pittsburgh. So here's a brief introduction about TAL. So TAL is short for Tomorrow Advancing Life. It's an edtech company that operates on the basis of smart education. It serves public education, empowered private education, and explores new education models for the future on a global scale. So as we all know, our experience of the world is multimodal. We see objects, hear sounds, feel texture, smell odors, and taste flavors, and then come up to a decision. Multimodal learning suggests that when a number of our senses are being engaged in the processing of information, we understand and remember more. By combining these modes, learners can combine information from different sources. So specifically in this talk, I will focus on discussing learning from multiple modalities, including language, images, and sounds. When it comes to the topic of machine learning or deep learning, a large body of research work are dealing with learning data representations. The effective representations can solve the majority of industrial machine learning problems. So in this talk, I would like to share some of our experience about bringing together information from different modalities and achieve better and more effective data representations. So here is the outline of my talk. So in the first part, I will talk about the multimodal learning for audio and language representations. And in the second part, I will talk about the robust language learning with the noises. And in the third part, I will talk about the educational multimodal machine learning applications we build at TAL. And the last part, I will conclude and outline some future outlooks. Okay, so the first part. So the first part is the multimodal learning for audio and language representations. So there are tons of rich information contained in both language and voice. The language focuses more on the content, and the voices contains extra emotion and feelings. Information from both modalities are very useful when building practical machine learning applications. So let's take speech emotion recognition as one example. The speech emotion recognition task is given an audio clip of spoken sentences, decide what emotion it is. The traditional approach handles such multimodal tasks usually fall into the late fusion paradigm. As you can see, we first get a transcription from the audio signal, then we extract sentence level embeddings from both linguistic and acoustic information respectively. Once we get these embeddings, we directly apply a fusion technique, for example, like a concact, to get the fused representation and use it for emotion predictions. So the above approach is simple and effective. However, we would like to make it better. At TAL, we don't want to unconsciously concact the sentence level embeddings from two modalities. We come up with an idea of conducting fine-grained multimodal learning. Specifically, we first conduct the temporal alignment, which, as you can see here, we align the pronunciation of each word in the audio stream. We use existing alignment tools to get the start and the end timestamps of each word in the audio signal. And then we apply the min and max pooling to extract the word level embeddings from the audio signal. After such temporal alignment, so after using such temporal alignment min-max pooling operations, we get the same number of words. We get the same number of words embeddings from both modalities. Okay, so once we have the initial embeddings from both audio signals and the transcription, we conduct embeddings fusions by cross-modality excitement. Specifically, we use the sigmoid function as the excitement function, and we use the embeddings from one modality to compute the excitement weights of the embeddings of the other modality. In such a way, embeddings from one modality are weighted by the importance from the view of the other modality. So here is the overall framework of our proposed approach, which consists of 4 important blocks. As you can see, they are colored. So the first block is in the orange, which is the initial acoustic and semantic encoders. And the second part is in the purple, which align the frame level acoustic information with token level embeddings. And the third part is in green, and which is a cross-modality excitement. And the last part is about the final predictions, which we extract sequential information from the field's embeddings. Okay, so in the experiment sections, we validate our approach by the 2 commonly used dataset, IEM, MOCAP, and the RevDis. So these datasets are standard test set for speech emotion recognition, and also here are some experiment settings. So here the result demonstrates that our approach is superior on prediction tasks for multimodal speech utterance, and it outperforms a wide range of baseline in terms of prediction accuracy. So furthermore, we conduct detailed ablation studies to show that our temporal alignment min-max pooling mechanism and the cross-modality excitement significantly contribute to the promising result, as you can see from the table. Meanwhile, in order to encourage the research reproducibilities, we have open sourced our code at the following address. Please visit our GitHub webpage. Okay, so in the previous work, I briefly talked about directly learning embedding fusions from 2 modalities. However, there are lots of work going on beyond that. So nowadays, as you may heard, pre-training becomes a buzzword, and it is prevalent across many research areas. So here is a graph showing the standard machine learning workflow with pre-training. Typically, a large-scale model is pre-trained on some unlabeled data, such as bird. Then for conducting predictions for specific tasks, we conduct fine-tuning with task-specific dataset, and the objective is optimized with task-specific loss. So BERT is probably the most popular pre-trained language models. Here is a picture I grabbed from the internet, and as you can see, since BERT was invented in 2018, many improved versions are developed. As you can tell from the model names themselves, lots of existing researchers focus on combining both the visual and the language informations. So the little has been done for utilizing information from audio and the language modalities. So here, I would like to introduce a model called Zitao, which is a pre-training cross-model transformer we developed at Tao for building practical machine learning solutions in education scenarios. So here is the overall model architecture of our proposed approach. Our cross-model transformer is built upon the standard encoder-decoder transformer architecture, and the left part is a standard. Sorry, and the left part is the standard transformer encoder, and the And on the left, there are several modifications on the decoder part. Okay, so here this is one key component in our Zitao model. So in our approach, the key component is a multi-head cross-model attention, which builds the intrinsic connections between the language embeddings and the acoustic embeddings. As you can see from the equations here, we use the language embeddings as the key and the values, and use the acoustic embeddings as queries in the standard attention formulations. In such a way, we are using the learned language representation to represent the acoustic information. In the loss part, we combine the standard mask language modeling loss and the mask across model acoustic modeling loss, which is used the weighted language representation to recover the masked acoustic information. With these two loss functions, we do the pre-training for the audio and language unlabeled data. So once we have the pre-trained model and we want to use it for fine-tuning, we apply the standard cross-entropy loss. Meanwhile, in order to capture information from different modalities, we design an orthogonal regularizations. The orthogonal regularization will prefer the representation learned from two modalities dissimilar. Okay, so we conduct the pre-training with two sets of parameters, as you can see here. This gives us two model variants, a base one and a large one. So our Zitao model is evaluated on three well-studied tasks, including emotion classification, sentiment analysis, and the speaker verifications. And all these relevant results are listed here, and apparently our model achieves the best performance. So furthermore, we conduct the detailed component analysis to well understand the proposed model. And due to the time limit, please check the details in our EMNLP papers. Okay, so in the second part, I will talk about the robust language learning with noises. As we all know, so if in order to build the practical machine learning solutions, we have to make sure the model works in the noisy environment. So here I just list some typical applications in education scenario. So here for this one, this is about automatically grading for the mental math question or question search. So I put an imagination here, an animation here. So you can see we have to take a picture of an image and we do the search. So as you may imagine, so there are a lot of corner cases when the user takes pictures, right? So here is much more applications from PhotoMath, Microsoft Math, and ADIA, which is created by Pearson. So all these are similar. It analyzes the picture taken by the students or the parents. Okay, so and also here it is an example I grabbed from Grammarly, which is about auto essay gradings. So usually students upload their handwritings, and the tools have to analyze what's the word written by the students, and also conduct the NLP tasks to analyze the essays. Okay, so here I took an image from the internet, which basically shows the OCR result from Amazon tax track, which is a public OCR service made by Amazon. So as you can see here, the result is not that good, even though the handwriting is okay for human to read, right? So when the NLP meets the OCR, there are a lot of troubles. So the recognition errors bring a lot of challenges for the downstream NLP tasks. So how does the existing approaches solve these problems? So the existing approaches solve this problem from two directions. The first one is pre-processing. So people hope to use the pre-processing modules for noise reductions. So we can either use the spell checker to correct the OCR errors, or we use the GEC tools, which is short for grammar error corrections. And also sometimes people rely on the large scale language models, to correct the OCR errors. All of this method doesn't work really well in reality because usually these kind of errors they don't consider the OCR error distributions. And also the second direction is people do the data augmentation through the adversarial training. Adversarial training is quite popular nowadays, and the people can do the white box attack or the black box attack. Basically, people want to find which part of the word is more like so people want to find which word in the sentence should be attacked. So here is a brief comparisons for the existing approaches. Apparently, both standard approaches, they don't consider the OCR error distributions. So that's kind of the realities. So here we took two standard OCR errors. The first kind of errors is token or char level errors. As you can see, the examples here, people, the OCR engine, they just cannot recognize some letters, right? Or characters. And the second type of error is the span level errors. The span level errors is more tricky. It's due to because the OCR engine usually have a language model at the end, and it may the recognition of the current letter will affect the subsequent letters. Okay, so in this work, we want to kind of build the robust NLP applications under the OCR settings. So in order to get a robust NLP models, so we want to simulate the OCR noises. So here we came up with 3 ways to generate the OCR noises. The first one is the rule-based simulations. So basically, we just make the insertion, deletion, and substitution edits to simulate the OCR errors based on some word or character distributions from the real dataset. And also, we do the attack-based simulations. So the attack-based simulation just replace tokens with synonyms at the weak spots. So both the rule-based simulation and the attack-based simulation, they kind of focus on the token or char level errors in OCR. And the third type of simulation is modal-based. So basically, we train the sequence-to-sequence neural models and on the parallel data of human transcription and the OCR transcription. So the model-based simulation, they just focus on the span level errors. Okay, so with the simulated data, we can train our model robustly. But after the data simulation, we get tons of data, right? So and we want to kind of in each training iterations, we want to find the really hard examples which helps the model training. So so here we design a practical heuristic about hard example mining. And each iteration, we use the current model to compute the representation of the noise-free sample and the simulated noise versions. And we select such pairs. We compute the cosine distance between the noise-free samples and the simulated noisy versions. And we select the sample pairs with the largest cosine distance. So this helps a lot, actually. So this give us This helps us select the effective training samples at each iterations. And in the second heuristic we have is we apply the stability loss. The stability loss is instead of the standard loss like such as the cross entropy loss, it add one extra component. So the extra component minimizes the disagreement between the model output and minimize the model outputs for the clean input and the noisy input. Okay, so after putting all these things together, so we have our framework. It basically have three components. The first part is noise generations, as I described before. The second part is how to select the hard training examples. And the third part is we add the stability loss into our optimizations. Okay, so in the experiment part, we use the data set. We use the data set in educational scenario. We actually have three data set all about rhetoric figures. So we have metaphor data set, we have personifications, and we have parallelism. So we have these three data set, and we test the result on two public OCR engines, which listed here, and the noise rate for these two OCR engines are different. The first one, the Hanver OCR is not its noise rate or it's at about 3%, and the Tau OCR engine is about 6%. And also we also open source all the data and the code at the following address. Please see our code here. And here is the result here. And we also choose some strong baselines, and as you can see here, in the majority, if we look at the F1 and under majority settings, our model achieves the best performance. And the details analysis can be found in our EMNLP paper. Also, we conduct the ablation studies to check the impact of our two heuristic, the hard example meaning and the stability loss. And as you can see here, with these two heuristic, we get quite a large performance gains. And at the end, we also check the how robust it is under different noise levels. Since the OCR engine we choose, it only has the noise level at 3% and 6%. So here we simulate more noises. And as you can see here, the performance dropped quite a lot as the noise goes up. But under the as you can see here, under the 10%, when the noise ratio is under 10%, the model kind of is pretty robust. Okay, so this is just one example when we build a practical multimodal machine learning solutions in the educational scenarios. And as we all know, the real world noises are way more than OCR errors. So here I just show another example. So as you can see here, I put a paragraph of text. So people may still read the text, right? So for example, according to a research at Cambridge universities, it doesn't matter in what order the letters in a word are. The only important thing is that the first and the last letter be at the right place. So I don't want to read all the sentences, but as you can see here, I can read the sentence. But if you look at the sentence closely, you will find that every single word is spelled wrong. So this is called the Cambridge sentence. So according to a lot of research, people can read the Cambridge sentence, but machines are not. So if I copy the sentence into the Google translation system, as you can see here, the translation engine is totally destroyed. You cannot get the result. So we build some machine learning models to do the robust word recognition, which is to correct the word like the word in the Cambridge sentence. So here, our model consider two types of information. The first is the child-level sequential dependence. It's very intuitive. For example, for the word whole, we know the letter W and L, they rarely happens together, right? And also we want to capture the word level sequential dependence, which is the linguistic information within a sentence. So based on these intuitions, we build a model called MULT, which is a model for which is our proposed model for robot word recognition. And I don't want to introduce a lot of details here. For people who are interested in our work, please check our AAA paper last year. Okay, so in the third part, I would like to describe some very cool and successful educational multimodal machine learning applications at Tao. So as we all know, classroom, lot of educational settings happens in classrooms. So when we talk about education, the first thing pop in my head is classrooms. So nowadays, classroom has evolved into many different forms. Mainly can be characterized in two forms, offline and online. As you guys can see here, on one hand, the traditional offline classrooms have been digitalized. On the other hand, students can use the live streaming to take classes with thousands of kids together, or they can just learn knowledge by watching animations. So here, this is the first application we built here, which is classroom activity detection. So as you can see, the picture here, this is some real pictures I took from the offline learning center at Tao. So we have a small classrooms, and the one student and one teacher sit in the classroom. They are doing the math tutoring. And we have recording devices to record the entire videos in each learning room. And the class activity detection task is we want to build machine models to split which part of the voice is the teacher talk, which part is student talk, which part is the noise, is no voice or noises. So this is a pretty useful and it's a pretty useful task, but it's very challenging because we have no other informations from the data. And so the first solution we came up with, we use the voice biometrics, because the number of teachers is well controlled. And for each teacher, we ask them to record several clips of their voices, and we want to build the voice biometrics. So here is the solution. So we collect teacher vocal samples, and we use a VAD to process the voice, and we do the feature extractions, and we learn the feature the embeddings from the teacher vocals, which become the teacher's vocal biometrics. And we do the similar things for the entire class recordings. And after we got the vocal imitation from both the teacher vocal samples and the classroom recordings, we conduct the representation learning through DNN, GRU, LSTM, or transformers. And then we kind of aggregate all the embeddings, and we conduct the attention prediction, which is we compute the similarities between the biometrics and the classroom recordings. Then we make predictions. So the work is published in AIED last year. This is the first attempt. And then we want to see what we can do if we don't have the voice biometrics. So here we did another cool thing is we built something called the multimodal attention layer, which basically is which is solving the classroom activity detection problem in an unsupervised fashion. So what we do is, given a long audios from the classroom recordings, we first cut the entire audio signals into small segments. And since the classroom only have the teacher and only have one teacher and one student, we use the acoustic features to conduct something like clustering. And we cluster all the audio segments into two clusters by the voice features, by the acoustic features. And once we have these two clusters, we have tags, right? So we know during the class that what the teacher speak and what the students speak are different. So we use the text features to do the predictions. So basically that's the idea under our multimodal attention layer. So the details about our model is published at the ICASP last year. If you are interested, please check our paper. Okay, so the second, so this is the first applications, and the second application we build is multimodal feedback generations. So nowadays, here. So nowadays we would like to generate some feedbacks from the multimedia. So for example, the students are writing their homework, and the homework submission is asking their parents to take videos of the entire to ask the parents to take a short video of the students. And the student, during that video, the students kind of think aloud, and they solve the homework problems. And from our side, we get the videos which contain the images, audio, and text. And we would like to generate the feedback from the video. So in this work, so we kind of build a multimodal feedback generation engines, which consider information from text, audio, images. And we design a modality gate which control which part of information is utilized to generate the feedback. And as you can see here, we have this is the performance of our PMFGN model, which has the best performance under a wide range of the natural language generation evaluation metrics. So the details of this approach is published at the Colin last year. And the third application is the assessment tool we built, which is called the spoken language proficiency assessment tools. So what it does is, we have a lot of tasks involves the vocal and the language. So here, this is one task. It calls the verbal fluency task. So here's one example. So we have a student, and we ask the student to answer, if we want to cut a loaf of bread into 20 pieces, how many cuts do you need? So in this task, we don't really care about the answer itself. We care more about the process, how the student solve this problem. So here is a short videos.
我们来看这一题，这一题是切法式小面包，就是说，你看这个是切了10下，再加上原来没切的这一段加1，那就是11段。这一题是我一共有20段，请问我切了几下呢？是说我
So I won't play the entire video, but as you can see here, the students are thinking aloud, and the student is thinking aloud, and she is solving the problem. So basically, we build a bunch of machine learning models trying to analyze the videos and give the full assessment under different dimensions to comprehensively evaluate the performance of the student. So basically, the assessment tool we built from the 6 dimensions They are verbal fluency, topic relevance, coherence, vocal emotion, post interaction, and vocabulary diversities. All these 6 dimensions are evaluated by the machine learning models, and we also build. And here's one example for our topic relevance model, and we use the transformers to compute the similarities with the cross multi-way attention networks. And also the solution can be, people can try our solution either at the following web link or through our WeChat mini programs. Okay, so that's a bunch of very cool multimodal machine learning application we built at Zitao. And at the end, I would like to have a quick conclusions. So here, as we all know, so the development and application of AI is bringing immersive and rapid change to almost every aspect of life. So I show you a lot of AI application in education, and I really believe that there are a lot more coming in the future. And here, this is a bunch of papers we built where we published in the past 2 years. And if you are interested in the details in my talk, please see our papers. And at the end, I would like to have a short, quick advertisement. And we are hosting the 3rd international workshop about AI for education. And the next year we will have it at AAA 2022. So please contribute to our workshop. Okay, so thank you very much.